This tutorial, this is David Okot. I want to take you through the topic of horizontal shear stresses. So these shear stresses normally occur in beams which are horizontal structural members. We know that when external loads are applied on a beam, shear forces are set up in this particular beam. From these shear forces, the beam will tend to resist them, and that resistance will be caused by what we call the shear stresses, which will be acting on longitudinal layers of the beam. So because of this, then they set up what we call the horizontal shear stresses. Normally, the main formula governing the horizontal shear stresses is given by tau. Tau is equivalent to F, which is applied shear force or the maximum shear force, multiplied by the area of the section, beam section, times distance to the center of that area of consideration, divided by the moment of inertia. Since beam is a horizontal member, this moment of inertia I is Ix multiplied by the breadth of the section. So we are saying from this that this one here is a applied shear force, or if you like, you can say the maximum shear force. This is the area of section, area of section. This is distance from neutral axis to center of area measured vertically. Remember, it's a y measurement, so it's measured vertically. This is the moment of inertia of the entire section. Moment of inertia about x-axis, and then finally this is the breadth. Breadth is same as the horizontal dimension of the section. Breadth or horizontal dimension of the section. Then from there we can look at shear stress distribution for different sections. So we beams normally take different shapes or sections, and the most common ones we have the rectangular, I section, T section, and sometimes we can say miscellaneous section. But let's look at a rectangular section. Like, how does the shear stress distribution happen for? So this is shear stress distribution. One, we start with rectangular section. Now, what happens for rectangular section is that the neutral axis will occur at the geometric center of our section. So if I have my rectangular section here, and remember, for a beam, the vertical dimension should be higher than the horizontal, because the I, moment of inertia, which is one of the important parameters of the beam, is normally highest when D is greater than B. So if I have my beam section like this, so my neutral axis will be at the center. So this is my neutral axis. This dimension is B, and the vertical one is D. So from here to here is D. Now this will be D over 2, D over 2. Now for the case of a rectangular beam section, it happens that the shear stress distribution takes this particular shape. It has a maximum value. So this is where we have the maximum value. Then it has 0 at the top and 0 at the bottom, but we have a value of maximum shear stress at the center of our beam section. And remember, this maximum shear stress at the neutral axis is given by 1.5 multiplied by the average shear stress. How do you compute average shear stress? You take the applied force divided by the area, which is applied force F. Area, we can have it as BD because our rectangular section has dimensions B times D. And in design of timber, this way you will appreciate the use of this maximum shear stress. During design of timber beam, you will find that when we are checking the compression stress at the support, we use the maximum shear stress is given by 1.5, the average shear stress, which comes from the applied force or the reaction FV divided by B times LB, where LB is if it is a wall, we call it the length of bearing. So this concept in structural analysis is very important when you come to real design of timber beams. Now, section number 2, we can look at what we call an I section. So that is a rectangular section. Then 2, I'll move to an I section. Just from the name, an I section is basically a section that takes the shape of capital I. So if you have that, so this is what we call the I section. So this is, sorry, it's not that good, but that is I section. Step number 1, you have to do what? You have to establish the position of neutral axis. Remember, for I section, we have this is a B and the whole of this is D. This is most common in steel section. During design of steel beams and steel columns, we'll encounter how the I sections comes about. Remember we said I section is the best structural efficient shape or cross section. Now if we can have a position of neutral axis as at this point here, just assume it is here. This is my neutral axis. I know so far you know how to compute neutral axis. Neutral axis is a line that passes through the centroid of this particular section. So the horizontal line through the centroid of the section is what we call the neutral axis. Now we know for I section, the web is normally the middle section, which is sandwiched between two flange, which is the top and bottom flange. Then D, capital D, we call it the overall depth. But now the distance from the bottom side of the top flange to the upper side of the bottom flange, we call it small letter D. So this is this one here. In design of steel sections, you will see it is given D. The same case, half of B, capital B, we call it small b, which is a half of, but that one will come at that particular time. But for this case, I just wanted to illustrate that. Now here, for the I section, we have what we call the salient points. Salient points are points where you need to plot the values of shear stress. One of the salient points is the top of the top flange and the bottommost part of the bottom flange. At those 2 points, the value of shear stress is 0. Remember the vertical line I've drawn, it indicates the value of shear stress at that point is 0. So the extreme top and extreme bottom, the value of shear stress is 0. Now from there, you go to this point here, this point where now the junction between the top flange and the web. Now there you will plot one stress in the flange part. After that, still at the same point, you plot stress in the web part. Because web is narrow, the value of stress will be higher. That is why you find that at the same line through the junction, we are plotting 2 points. First point is due to flange and the second point is due to web. Then we'll go to the neutral axis, which will give us the highest value of shear stress. Then we'll come down here, the intersection between the web and the bottom flange, we also plot there 2 points, and then finally we said it will be here. So it will take a parabolic shape, just like the rectangular one. It will take a parabolic shape. So I'll plot from here, it comes here, it goes here, it comes here, maximum value, it comes back here, here, and then here. So for the case of I section, that is how it will be. This is where we have the maximum shear stress at the neutral axis. Then finally we can look at the shear stress distribution in a T section. That will be our number 3. This is T section. Just from the name is basically capital T. Now for T section, it takes this shape. This is our T section. So for the T section, step number 1, I have to do what? I have to compute and know where the neutral axis is. So maybe let's just make an assumption. This is my neutral axis. We compute it by determining the value of the centroid. So once I have the neutral axis, I have now to plot how many points? 1, I'll plot at this point here, topmost. Then at intersection between this line here, between flange and the web, and then the bottom part here. No, without forgetting the neutral axis. So what is going to happen? Just like we had in the I section, the extreme top and bottom will have values of shear stress as zeros. So you find this point will be 0. 0 means I plot on this vertical line, and also this lower point will be 0. And then for the case of intersection between web and flange, I'm going to plot 2 points. The first point is due to flange, then the other one is due to web, and then finally I plot at the neutral axis where I expect to have the maximum value, and then here it will come back to 0. So this distribution will take this shape here. So it will have this particular shape. So it will start from here, comes here. This is a top flange. It moves here, web, then it comes to highest value at the neutral axis, and then it goes to 0 where still maximum occurs at the neutral axis. So if you have been very keen, you realize that the value of shear stress is maximum at neutral axis for all the section, irrespective of whether it is a rectangular, is an I or a T section. And at the intersection of web and flange, you have to plot 2 points. 1, it is shear stress in the flange at that point, and 2, shear stress in the web at that point. So on that line that is coming out of the intersection of web and flange, you find that you have to do what? You have to plot 2 points. Remember we said that shear stress is given by F AY over IB. And maybe what I had forgotten to tell you is that this component here, we call it first moment of area. First moment of area. Why first moment of area? Because we are taking area times its distance from the neutral axis. If I multiply it another time, like I have a times y squared, then I call it second moment of area, which is the same as what? I. Because I is either moment of inertia or second moment of area. But now whatever I have in the numerator, the shear force value times the component AY. A is area, Y is its distance from the neutral axis. So the two when put together, you call it first moment of area. Thank you so much. See you on tutorials now. I think this was just to introduce you, to give you a brief of what the shear stress is. Thank you. Goodbye. See you again.